All right, recording is rolling. Welcome to Friday, September 29th. You guys just turned in your chapter 4 puzzles. Thank you for doing that. We did cover all those in class also, so let's see about those. You guys, this take-home quiz, dynamic take-home quiz is due on Monday. And so my other classes were wrapping up, well, we're all wrapping up this unit. My other class and how to do some activities, so I'll show you guys real fast what we're doing. So you guys remember we started this unit with these spring cells. I had you guys do like 10 mini labs, right? We figure out how forces work, and then we went over like the textbook formulas and whatnot, right? And so how these spring cells work is based on Hooke's law. Right? You apply some force, it stretches some amount, right? But how much it stretches depends on how thick is the spring. Right? That's what's called the spring constant, right? Which is like the slope of this line, right? So if it's a really shallow slope, that might be like this blue one, right? Little force stretches it a lot. If it's like a really steep slope, that's a huge force takes to stretch just a little bit. And then the brown ones are kind of in the middle, right? It's like a medium force. All right. So like the slope of this line. So I'm having my other classes figure out what is the spring constant for each one of these. Guys, what's the units? What do you think the units are for spring constant?
Newtons
per
newtons
per meter. Newton per meter. Yeah. So Newton per meter translates how many meters stretch to the force in newtons. Okay. So now this is going to be like some number of centimeters. So maybe I could divide by 100 to get the number of meters, right? Let's see here. Here's a calculation from earlier today. We took Hooke's law, F equals kx, rearrange it, k is f over x. So here, if I apply a 20 Newton force to the gold one, it would stretch to 2.4 centimeters. So you can divide that out and say, okay, spring stiffness is about that much. Okay. So anyway, we're gonna skip the activity, but my other class haven't do that. Right. Speaking of spring type objects, we switch over here. There's this really cool video I want to show you guys that I never quite got around to. So let's slip this in fast, right? Slinky drop. Some of you guys have probably seen this, right? What happens when you drop a slinky? Let's take a look. Ooh, let's see if slow-mo from the side. Whoa, look at that. Whoa. Right? And see how it takes some time for that information to catch up down below, right? Hey, do you guys think in general, it takes time for anything to travel, right? There's a cosmic speed of light is the cosmic speed limit, right? So if NASA wants to communicate with the probe on Mars, it's going to take a few minutes for the info to go there and also back, right? Trying to like navigate with the video and whatnot, right? But even just like if you're hearing my voice right now, is there a tiny time delay like from my voice to your ears? Yeah, because it takes some time to travel a distance. That'd be like the speed of sound. Like speed of sound would be limiting, right? It's a lot slower than the speed of light. That's closely related to this right here. All materials, if you press or stretch on them, they'll compress a little bit or stretch a little bit, right? So all materials have a spring-like quality to them. Now, a slinky, you could have has a tiny spring constant. A block of concrete, you could also think of as a spring. It's just like a really stiff spring, right? It takes a huge force to compress it just a little bit, right? But all materials are like this. So there's time delay. In this case, like a free body diagram of a point near the bottom, got the tension force up, the weight down, right? It's balanced out. And yeah, it takes a time delay for that information up the top at least to reach the bottom. So that's pretty cool. That is from a channel called Veritasium. I've also got another Veritasium queued up. Let me bring this up here. Where are you? Here you are. Magnus effect. Okay. So in baseball, how does a curveball curve? Or if you kick a soccer ball with some spin, maybe you can get it to spin like into the goal. Right? There you just drop the basketball straight down. The air is pushing around a little bit, but it basically goes straight down, right? But what if puts a little spin on this, a little bit of spin? What's gonna happen? Oh, look at it go. Well, let's deal with that. Goes back and does that again. We fast forward a little bit here. Fast forward. The Magnus effect. So get a spinning ball and it'll push the air around it. And this creates a pressure differential. Something called Bernoulli's principle. It's kind of related to a fast moving fluid, like decreased pressure. Anyway, there's a pressure differential. You guys know pressure is force per unit area. Rearrange that. Pressure differential times this cross-sectional area creates a force. It's going to push the ball in a certain direction. All right, so I just wanted to slip that in. Oh, whoops. Go back here. All right, one more thing. All right, so main thing today, though. All right, here I want to give you guys time for this. Okay, so you guys have laptops up. That is awesome. Just go to Google Classroom, and here's this link right here, CR4CR. I give you guys the rest of class to do that. And yep, that's gonna round out the week. You guys turn in your take-home quiz on Monday, and then on Monday, we're going to start a new unit. We're starting Unit 3 by AP's book, which is going to be centripetal force, circular motion, gravitation, and orbits. It's a bunch of little things put together. All right, that's a wrap on this video.